Hello everyone, myself Sriram Ramesh. I'm going to give a lecture about challenges in multi-core processor. The scope of this lecture is not only limited to challenges in multi-core processor, but also will provide exposure to how these challenges are handled in real world. To make this session interesting, I'll be explaining certain concepts with the example of processors, discuss some novel solutions for some well-known problems, and talk about some emerging concepts which has the potential to solve these problems. First, I'll show you the outline of this lecture. The image here shows the powerful processor of IBM. It is the first general-purpose processor that featured multiple processing cores on the same CMOS time. It was released in the year 2001. I will now explain why the industry has started to move towards the multi-core processors. As the CPU speeds rose to 3 to 4 GHz, the amount of power required to go faster has started to become prohibitive. The primary reason being factors such as heat dissipation and leakage current. It was noted in an IEEE review that power consumption increases by 60% with every 4 MHz rise in clock speed. But using the dual core approach, you can get a significant boost in performance without the need to run the clock at higher frequencies. Let me provide an example to illustrate this behavior. From the table column, we can see that the X5660 has the same electrical power as that of X5560, but it will have 50% more computing power. This is due to the two additional cores X5560 has. Another reason to shift to multi-core processors is the limitations of instruction-level parallelism. It includes the control dependencies, data dependencies, and the long latency of cache misses. I will now delve deeper into the challenges of multi-core processors. First, power and temperature. Power consumption is a major design issue in modern microprocessors. As the number of cores increases, the power consumed by it also increases. The unnecessary power consumption can be reduced by shutting down of cores which are unused. This can be done by the power control unit. Another method to reduce the power consumption is to use the dynamic voltage scaling. DVS allows systems to work at different voltages or frequencies. Research from research work shows that systems not implementing DVS compared with systems implementing 2 or 5 levels of DVS achieve energy savings by 35% or 51%. We will now look at a case study of a cell processor which follows a curious way of temperature monitoring. The cell processor consists of 64-bit power processing element, multiple synergistic processor elements, a memory interface controller, caches, interfaces, buses, and a pervasive unit which supports extensive test, monitoring, and debug functions. From the thermal diagram, we can see that there is a higher heat flux from a smaller hotspot which hinders spreading of heat across the silicon substrate. The cell processor consists of a linear sensor and 10 local digital thermal sensors. The linear sensor is used to measure the die's global temperature and adjust the cooling accordingly. The digital thermal sensor provides a warning in case of a temperature increase. In that case, a thermal management is carried out. The thermal management can be done using global clock gating or by DVFS, in which voltage and frequency scaling is applied to reduce the temperature. Now, moving on to the cache coherence and cache sharing. First, we'll see about cache coherence. The multi-core processor chip consists of multiple single-threaded cores, each of which has its own private data cache and a last-level cache that is shared by all cores. In a shared memory system, each of the processor cores may read and write to a single shared address space. Thus, it can lead to an inconsistent data. The cache coherence problem can be explained with the help of an analogy. Now, consider a student checks an online course schedule of computer architecture course being held at room 152 and copies that information in her notebook. Now, the university registrar decides to move the class to room 252 and updates the online schedule. But the copy in student's notebook is now stale and an incoherent situation has now arisen. How do we prevent this type of incoherence? This can be solved by implementing the cache coherence protocols. Cache sharing. Conventional CPU schedulers assume that CPU is a single, indivisible resource and that if threads are granted equal time slices, those threads will share the CPU equally. But in multi-core processor, cache sharing depends solely on the cache needs of the core running threads. And unfair cache sharing often occurs. This will affect its miss rate. From the figure of multi-core processor, we can see that the core 2 unfairly shares the L2 cache. This problem can be solved by implementing the scheduling algorithms. I came across an interesting scheduling algorithm by Dr. Alexandra Fedorova named as cache fair algorithm. It redistributes CPU time to threads to account for the unequal cache sharing. If the thread's performance decreases due to unequal cache sharing, it gets more time and vice versa. The challenge in implementing that is that there is only limited information from the hardware to know about the unfair cache sharing. I won't go deep and explain the work, but I would recommend everyone to go through the complete research work if you are interested. The next challenge is multi-threading. Next challenge is multi-threading. The ability of the CPU to execute multiple processes concurrently is called as multithreading. I must clarify one thing here. Many confuse parallelism with multithreading. Parallelism is using a set of resources to solve the problem by dividing the work. Multiple processes are working at the same time on multiple CPUs in parallelism, but in threading, multiple processes are working at the same time on single CPU. There are three types of modules in which multithreading can be implemented. Those are simultaneous, coarse grain, and fine grain. Now I will explain some emerging concepts. Scouting threads. The basic idea is to let the execution of the hardware thread continue even if normally it would stall. For example, the processor switches to a mode called scouting while waiting for the data to be fetched and execute instructions out of order that are not dependent on the result of the instruction that causes stalling. Once the stalling is over, the execution is again resynchronized. Now, we'll move on to helper threads. It consists of a separate core that would monitor the traffic to and from a specific core, recording memory access patterns. This information is stored, and whenever it is observed again, the cache is preloaded ahead of time. Now we'll Memory bandwidth is the next bottleneck that needs to be addressed in the future chips. More main memory and other caches are needed for multi-threaded multiprocessors. Now we'll see about some upcoming technologies for improved memory system. 3D memory stacking. In 3D memory stacking, a completed computer chip such as DRAM is placed on top of the CPU. In this way, the chips that were used to be centimeter apart are now millimeter apart. This provides improved bandwidth and reduced power consumption. Now we will see at memristor. This device can remember a voltage applied to it even after the current is cut off. This can pave way for computers that can never lose data. Now we'll move on to the next challenge, system bus and interconnection. Extra memory will be useless if the amount of time required for memory request doesn't improve as well. Redesigning the interconnection network between cores is a major focus of chip manufacturers nowadays. Example of system bus include hypertransport and quick path interconnect. I'll just talk about the features of these technologies which will help the multi-core processors rather than explaining them in detail. Now looking at hypertransport, it supports AC operating mode which allows bus to achieve longer distances. It allows link splitting which allows more CPUs to be connected without using any extra hardware. Hot plugging allows devices to be installed or removed while the bus is running. In dynamic link clock or width adjustment, the CPU can change its clock rate as well as the number of bits it transfers per second. Now moving on to quick path interconnect, it has reliability, availability and serviceability features inbuilt into it. It also has a smooth protocol optimized for low latency and high scalability. It also has packet and lane structures which enables quick completions of transactions. Now we look at the next challenge which is the parallel programming. The advent of multi-core processors offers the capability to run the programs in a parallel fashion rather than running them sequentially. But there are many problems when it comes to parallel programming. Initially, the transportability of the parallel program from one environment to other is a difficulty. Also, there is a lack of tools and technique for debugging and testing the parallel program. Now I'll be explaining about SWARM. SWARM is an acronym for Software and Algorithms for Running on Multi-Core. SWARM is a portable open source library consisting of basic primitives that provide framework for designing algorithms on multi-core system. In order to use the SWARM library, the programmer needs to make minimal modifications to the existing sequential code. After identifying the routines in the program, work can be assigned to each core using an efficient multi-core algorithm. Another parallel programming platform is CUDA. It's Compute Unified Device Architecture and it is used for the design of parallel programming in NVIDIA graphics processor. The next problem in multi-core processors is starvation. The multi-core multi-thread processors have made memory bandwidth a crucial resource, wherein each extra core or thread generates extra memory traffic. If the parallel programming is not executed correctly, one or more cores will starve for data. This can be solved by implementing the memory access scheduling algorithms. Another solution is adding starvation time threshold to identify the requests waiting for a long waiting time and serve them first. This method can be used to improve fairness. This lecture covers all the major challenges in the multi-core processor. If you are interested in learning more about this lecture, you can always use the references I have provided in the slides. And thank you for watching.